So I'm going to be showing how to derive the thermodynamic factor matrix, equation 132, from equation 130, which is the driving force. So we're going to start with the driving force equation here, which is the driving force of component I, which is equal to the mole fraction of component I over RT, multiplied by the derivative of the chemical potential of component I over dz. So first what we're going to do is we're going to write out the equation for the chemical potential component I. So that's equal to the standard chemical potential plus RT times the natural log of gamma I times xi. So this is the activity coefficient for component I. So that is taking into account, so it's a correction factor for our mole fraction of component I. It's taking into account non-ideality. So we're going to take this chemical potential equation and plug it in here for our derivative. So it's going to be equal to xi over RT multiplied by the derivative of standard chemical potential plus RT times the natural log of gamma I times xi. So when we take this derivative, this is a constant, so it will be 0 in our derivative. So let me write this out. So these come straight down. So this will be 0. We can actually pull out this RT from our derivative, and then we'll have left the derivative of the natural log of gamma I xi over dz. So now we're going to be taking the derivative of this part. So that will be, and we can also do some canceling of our RTs. So we'll have xi multiplied by the derivative of natural log of gamma I over xi times the derivative gamma I xi. And again, we can do some canceling. So now we're going to take the derivative of this portion, which is equal to, pull this out. So this is chain rule, so we're going to hold first the gamma constant, and then the derivative of xi dz, plus, then we're going to hold xi constant. We're going to take the derivative of gamma I over dz. So I'm going to write this out just so it looks simpler. So when you multiply the 1 over gamma I over, we have the derivative of our mole fraction in terms of dz multiplied by, or sorry, added to xi over gamma I times the derivative of gamma I over dz. So this can actually be written more simply, this part, because that is actually equal to natural log derivative, natural log gamma I is equal to 1 over gamma I times the derivative of gamma I over dz. So that's what that's equal to. So that's why we're able to plug in the derivative of a natural log of gamma I for this part. So we're going to go ahead and do that. Xi times the derivative of natural log gamma I over dz. So this part, we'll actually now be writing it out in terms of our mole fraction, so our xi. So when we expand that out, it'll look like this. We'll have the partial derivative of the natural log of gamma I over partial derivative of xi times derivative of xi over dz. So what this is here is that we are looking at the driving force of each individual component, and we're seeing how the activity coefficient of that component is changing with respect to the mole fractions of the other components. So that sounds confusing, but if I write it out in terms of an example, so let's say we have a 3-component mixture. So what that would look like is that for the first component, so for component 1, we would have that dx1 over dz plus the mole fraction of the first component times the partial derivative, the natural log of the first component's activity coefficient. And how that's changing in terms of the first component, plus how the derivative of the natural log of our first activity coefficient is changing with respect to the second component. And the same, how is the natural log of our first activity coefficient changing with respect to our third? How is it changing with respect to our third component? So this is, I would be in a 3-component system for our example, would be written out for each component, for first driving force, for the second driving force, and for the third driving force. These coming together is what is equal to the total driving force. So I'm going to write that out. So again, this whole part is saying that our total driving force is equal to the driving force of each component. And the driving force of each component is looking at how the activity coefficient for that component is changing with respect to each component. So this big portion here for our example of a 3-component mixture can be written out in the terms of matrix multiplication. So I'm going to write that out here. So how we took from this derivation, we expanded it out for the activity, to see how the activity coefficients from each component are relating to each driving force of each component, which we can then write out as a matrix multiplication. So this part right here that we're looking at, this part right here is showing our actually equation 131, so right in between. So this part is the thermodynamic factor matrix. What we're looking at here is this first component for each of these values, which looks at the mole fraction of that component times the partial derivative, the natural log of that activity coefficient in terms of the partial derivative of the component that we're multiplying by. And then also we'll see that in some points we have this plus 1. So in the places that don't have a plus 1, we can think of as having a plus 0. This value here, or here, or here, is the Kronecker delta. So the Kronecker delta says that if Ri is equal to J, then our Kronecker delta value is going to be 1. If our I is not equal to our J, our Kronecker delta value is going to be 0. So that's why here in our matrix we have the value that we're looking at, if it's, or the thermodynamic factor we're looking at, if it's in terms of the same mole fraction, then that will be a 1 value in front. So that's what the Kronecker delta is. So this part of the equation we derived is our thermodynamic factor, and this part is our change in the mole fraction of the other components. So this full equation is saying that our driving force is equal to our thermodynamic factor multiplied by our concentration gradient. And from that, we are seeing that our thermodynamic factor is equal to the Kronecker delta plus our mole fraction times the change in the natural log of our activity coefficient over the partial derivative of our xj. So this is how we get from equation 130 to 131, which is the thermodynamic factor matrix.